Welcome back to the chapter Real Numbers for Standard 10, and this is part 12. We will do some more problems related to the applications of Euclid's division lemma. Prove that n squared minus n is divisible by 2 for every positive integer n, or prove that the product of two consecutive integers is divisible by 2. For both, the method is same. Here consecutive integers means n, we can take n minus 1 and n. They are two consecutive positive integers, so n minus 1 into n will become, this is equal to n squared minus n. So now we have 2 is divisible by 2. So we will take let any positive integer is of the form, any positive integer is of the form 2q and 2q plus 1, because the divisor is 2, so the remainder will be 0 and 1. That's why it is 2q and 2q plus 1 for some integer q. Now we will take when n is equal to 2q. When n is equal to 2q, we have to find n squared minus n. N squared minus n, that is equal to 2q the whole squared minus 2q, so that is equal to 4q squared minus 2q. You can write this as 2 into 2q squared minus q. So you can, so this is divisible by 2 because you are able to write 2 into, so this is divisible, so this is equal to 2m, where m is equal to 2q squared minus q. So this is divisible by 2. Now when n is equal to 2q plus 1, so n squared minus n is equal to again 2q plus 1 the whole squared minus 2q, so this will become 4q squared plus 4q plus 1 minus 2q, so this is equal to so this is equal to two q plus 4q squared plus 2q plus 1, so this is equal to n 2q plus 1 minus of n is equal to 2q plus 1, so minus 2q minus 1, so this will become 2q, so then 1 is gone, so you will get 2 into 2q squared plus 1, so this is equal to 2m, where m is equal to 2q squared plus 1, so this is again divisible by 2. Therefore n squared minus n is divisible by 2 for every positive integer n. Show that the square of any positive integer cannot be of the form 5q plus 2 or 5q plus 3 for any integer q. This is an NCERT exemplar problem. So here to prove it is not of the form, now we will see what are the form possible. The same method we have to use. Let x be the positive, let be any positive integer. By Euclid division lemma, you can write a is equal to, if a is any positive, a is equal to bq plus r. Here we are going to take b as 5 because we have to prove 5q plus 2, 5q plus 3. So we take b is equal to 5. So a is equal to 5q plus r, where r is equal to 0, 1, 2, 3 and 4. So we'll start with let x is equal to, because we have to prove 5q and all. So let x is equal to 5m plus 1, 5m plus 2. When r is equal to 0, 1, 2, 3, when you put, you will get 5m plus 1, 5m plus 2, 5m plus 3 and 5m plus 4. So now case 1, when x is equal to 5m, x squared is equal to, so x squared is equal to 25m squared. So this can be written as 5 into 5m squared. So this is equal to 5q, where q is equal to 5m squared. Now case 2, when x is equal to 5m plus 1. So x squared is equal to 5m plus 1, the whole squared, so this is equal to 5 into 5m 5m plus 2 plus 1. So this is equal to, you can write this as 5q plus 1, or 5 into 25m plus 2m. So where q is equal to 25m plus 2m. So here it is 5q plus 1. Is 3 when x is equal to 5m plus 2. So the whole squared is equal to plus 4. So we can write this as 25. So I'll write this as 5 into 5m squared plus 4m plus 4. So we can write this as 5q plus 4, where q is equal to 5m squared plus 4m. So similarly, doing the same method, when x is equal to 5m plus 3, same x squared. So you get here 9. So here 9 should be written as 5 plus 4, so that 5 can be taken as a common factor. So you get this 5 plus 4. So this is of the format 5q plus 4, and again x is equal to 5m plus 4, also the same method. You will get here 16, you will write it as 15 plus 1. So that 15 can be taken 5 as a common factor. So you will get 5q plus 1. So now if you see, this is 5q, format is 5q, here the format is 5q plus 1, 5q plus 4, 5q plus 4, and here 5q plus 1. So you don't have the format 5q plus 2 or 5q plus 3 in any of these cases. So you can write square of any positive integer cannot be of the form 5q plus 2 or 5q plus 3. Prove that one of every 3 consecutive positive integers is divisible by 3. So let So it is given 3 consecutive positive integers. So let n plus 1, n plus 2 be 3 consecutive positive integers. So we can write n is equal to bq plus r, because, and here b is equal to 3 because we have to divisible by 3 we have to show. So we take b as 3. So we can write this as n is equal to 3q plus r, where r is equal to 0, 1, 2. So n will be of the form, now r is equal to 0, 3q, then 3q plus 1 and 3q plus 2. So now out we have to case 1, when n is equal to 3q, the 3 positive integers are 3q, 3q plus 1 and 3q plus 2. If you see here, only 3q is divisible by 3. So here 3q is divisible by 3. Now case 2. When n is equal to 3q plus 1, the 3 positive integers will be 3q plus 1, 3q plus 2 and 3q plus 3. So here 3q plus 3 can be written as 3 into q plus 1, and it is divisible by so you can write, so 3q plus 3 is divisible by 3. Now case 3, when n is equal to 3q plus 2, the 3 positive integers are 3q plus 2, 3q plus 3 and 3q plus 4. So you can write only this, 3q plus 3 is equal to 3 into q plus 1. If you see, these two are not divisible by 3. So this is equal to, so you can write 3q plus 3 is divisible by 3. So one of the every 3 consecutive integers is divisible, only one of the every 3 consecutive integers is divisible by 3 is what you have to prove. So in this you found only 3q is divisible by 3. So here out of this only 3q plus 3 is divisible by 3, and in this 3q plus only this is divisible by 3, hence proved. See you all with more problems in my next video. If you find this video useful, kindly subscribe, share it with your friends and leave your comments. Bye for now.